Good morning. So, we got the cloud working. Cloud working means actually we had two clouds. So, I was unhappy that we could not give a demonstration. So, I am going to show that to you. Whatever I tried to show is something that you can use in the class. Okay. Basically, our cloud crashed because the power was away for 1.5 hours, very long time, and our DG set is still not functioning. So, as a result there was a serious problem. So, let me now demonstrate. Remember I told you about 604 textbooks already coded in Scilab with 75,000 examples. So, let me explain it. I opened the cloud now. This cloud is, it will be cloud.scilab.in. Right now I am showing it through some other site. Okay, this is not where you will try later. So, let us try this. Let me try electrical engineering. I am going to choose control systems. I am going to choose BC-Co. Okay. Which chapter? I will choose frequency domain analysis. Okay. Example, I am going to select body plot. The moment I select the last one, it shows the code. All of you have studied about controls, gain margin, phase margin. You have the code. Now I execute, it produces the body plot, gives it to you. I can download it if I want, or I can close it. Okay. How many people are familiar with this topic? Okay, how many of you are, okay, I am going to give a quiz to all of you. All of you are caught now, right? I am going to give a quiz. Okay, I am going to look at this gain of the system, it is 2500, right? Numerator, I am going to change it to 5000. When I change it, will the margin go up or come down? It becomes more unstable or less unstable? Gain is higher. Okay, you will be able to compare your understanding with the result. So, it will become more unstable, that is correct. So, let us execute now. Note down the margins 14 and 31, right. So, let me execute. Okay, let me close. Margins are 8 and 17, previously it was 14 and 31. So, margins have come down, it has actually become more unstable. So, you can actually say what will happen if something, you understand. Okay, now we can select some book, we will run it live. For this you need internet. For the one I showed earlier you do not need internet because you can download the whole thing, keep it in your computer and then use it. You understand? You can download the entire textbook companion. I downloaded Procky's book for example, right. I also downloaded some other book, right. I have not logged in. You can use it. You want to choose some other topic? This is electrical engineering. Electrical engineering, you want to try something else? Let me show you something from Procky's. Electrical engineering, signal processing, DSP 24, book, Procky's and Modelica. Okay, let us say frequency analysis, plotting continuous time Fourier transform. Immediately code comes. I execute. Is it useful? Is it useful? Right? And we have it for 604 textbooks. 604 textbooks. If you want to, yeah, you can conduct a workshop yourself using spoken tutorials. And Scilab is 95% compatible with MATLAB. Everybody who knows MATLAB can learn Scilab within 10 minutes. And you have all the things coded already. And you ask them to run it. In any case, when you teach in the class, students do not have laptops. You will do it by hand. Instead, you are saying that we will do it by Scilab. That is all. What does it matter? They do not need Scilab at the time. For their learning, it will be useful. They may want to try what if analysis. What if the friction factor is reduced by 1/10? What will happen? What will happen to the pressure drop? If the rate constant is increased twice, what will happen to compositions of various chemicals? Various things. You can do what if studies. It's a very powerful tool from your textbook. And in case your textbook is not covered and you want to create a textbook companion on that, we invite your student to do it. You will have a smart student in your class. And how is it helping the student? Remember, whenever we host it, the contact details are mentioned. This is created by, this textbook is created by such and such person from such and such college. There was a student in IIT Madras who applied for summer internship in Japan. He wrote to us saying that because he did textbook companion, he got this Japanese internship. There was another student who wanted to go to Rutgers University in New Jersey, USA, and he applied for teaching assistantship. And they asked, how do we know that you can do programming? He sent a link. He got that. So it is actually useful, it recognizes your contribution. We recognize your contribution and you are helping lots of people. You are helping lots of people, right? So this is something I wanted to show you. Remember the other thing that I showed you, PFSS, partial fraction expansion. Remember I tried 27 examples, 27th I selected. When you click cloud, if the cloud works, it opens like this, okay. This is in chemical engineering process control. Remember this book Kofner in 4.2 final value theorem, they have given PFSS, you can see it here, okay. So I execute. I've got the transfer function, I've got the fractions, partial fractions. Okay, I'm going to ask you a quiz now. Why is it displaying only the denominator? What happened to the numerator? Why NUM is not displayed? Why is NUM, poly not displayed? Why DEN, something poly displayed? There is a semicolon. Excellent, that's all. So let's remove the semicolon and run it. Now NUM has come, right? You can change the values. You got a new problem, you can give it to students, you can give it in the lab, you can give it in the test, assignments, useful, right? From your textbook or the textbook that you used when you were a student, and we have it for 604 books with 75,000 examples coded. Okay, I will take 10 more minutes to finish what I wanted to say. I am going to show you some of the other things that we are working on, right? And then after that we will give a demonstration. We have R also. How many people know about R? So we have, if you see r.fossee.in, go to r.fossee.in. Once again we have the same thing, textbook companion. Remember, what do? For every solved example, give code. If you give R code, it becomes R textbook companion. Completed books, 23 books, various statistics books. Books in progress, various books, 38 books. So if you have a student who would want to contribute, invite them. OpenModelica, I told you it is 10 times more powerful than Simulink, 100 times more powerful than Simulink, okay. So we have a lot of things here, om.fossee.in. For every one of them we have spoken tutorials, you can learn yourself, and you can conduct training for your students using that, spoken tutorials. OpenModelica, completed books, what are these? These are textbook companions. For every solved example in the book, you have OpenModelica code now. This is OpenModelica textbook companion, right? How many books we have finished? 33 books. There are many books not done yet. So that's an attraction for your students, right? And to you in case you are interested. And books in progress, 21 books in progress, okay. We have also other things, for example if you see power systems power systems, completed power system simulations. You can actually simulate a power system using OpenModelica. In fact, there is going to be a demo of it by Biswaroop. You can see that IEEE 14 bus system implementation in OpenModelica. Here is modeling of IEEE 62 bus system using OpenModelica and OpenIPSL. Every one of them has the code. If I click this, it will download and run it in OpenModelica, and OpenModelica runs in this machine. OpenModelica runs in this machine, which is not very expensive, right? Similarly, in chemical engineering also we have something called completed flow sheets. Any chemical engineer here? May not be many, none, but in case there is, if you have a friend, you can ask acetic acid esterification, methanol water distillation, ethylene glycol production. If you click this, you will get the code. You run it, you have the flow sheet simulated. So why should you contribute? Reom Certificate, link to your work on our website. I have already told you this. Okay. DWSIM is another chemical process simulator. We have a large number of flow sheets. Let me show you that. In case you have chemical engineering friends, you can show them. Fossee.in, completed flow sheets. These are all various chemical processes. How many have we done? 124 chemical processes simulated. Each one will have a complicated things, right? Already solved, ready to go. Similarly, we have another thing called eSIM. eSIM is electronic circuit design and simulation. It's an alternative for PSpice, for example, may be useful to some of you. So in this, we have something called circuit simulation project, completed circuits, various circuits simulated already using this code, 58 finished, but then thousands to be simulated. So your students can participate, your students can contribute, and we give honorarium, we give certificate. More importantly, we give the link which your students can use. So many in completed, so many in progress, about 10, 11 in progress, but thousands to be done, all EE students, electrical engineering students, electronic students, please ask yours, they can all participate, right? It's eSIM. So we also have lab migration project. You want to migrate from PSpice to eSIM, we'll help you, right? And so on. So lab migration, every one of them. We also have anybody from mechanical engineering? Lots of people, right? Look at this. cfd.fossee.in, computational fluid dynamics. Do you have it? Is it of interest? So we have something called lab migration project. You want to migrate your lab from Fluent to this, we'll help you. Case study project I want to show you. Completed case studies. Okay, we have 28 case studies. 28 case studies already available. Okay. CFD analysis of a centrifugal pump, airflow simulation around a bullet, CFD analysis of bullet train, we seem to like bullets, external incompressible flow over hull of ship, and so on and so forth. Fantastic, right? Already done by students from various universities, colleges. We welcome this from your students, your smart students. We welcome this from you, from you. In every one of them, we actually explain procedure. See this first thing, it says procedure, and then procedure is explained. Then proposal, case study proposal, and so on. Every one of them we have explained. The only thing you have to remember is Fossee.in, Fossee, Fossee.in. Just show you that. So this has resulted in collaboration. We are doing a lot of work with collaborators. PLC, for example, this is something we built. Raspberry Pi based Open PLC we built, developed by Fossee IIT Bombay. We built 2 PLCs. We used 2 open source software packages and then sent the PLCs to Austria and Alabama, because one of them is from Austria, the other one from Alabama. They wrote the software, we created the hardware, we built it, we sent it to them. They said, hey, it works fine. Okay, so we wrote a paper together. So this is what we are going to do. We are going to conduct a workshop on OpenPLC. We are going to conduct a workshop on Arduino, like the way I mentioned. We are going to do Python next, R, and so on, but we will do it on Arduino. We will do a similar workshop on eSIM. We are going to do a workshop, teacher training workshop. Okay. In fact, to participate in teacher training workshop, the precondition is the faculty members should create a very simple low frequency oscillator and upload the Gerber file to us. Only those people will be permitted to attend the workshop, but then we will give the PCB for you to try out. Okay, this is OpenPLC work. Okay, it leads to collaborative research, so we wrote this with our Swedish team. So open source is a great concept. It can work in a country like India too, right? In fact, it is more suitable for our country, wherein we have lots of manpower, we have lots of people, we have lots of students, more than anybody else, maybe with the exception of China, right? We probably produce more engineers than even China. We have lots of people who can contribute, but then our investment cost is capital cost is very expensive, buying expensive software, right? That is not possible we are not economically well off. So for us, I would say, I have written it wrongly, it can work in a country like India too. In fact, it's most suitable in a country like India, right? Fossee promotes IT training. We hope to train a large number of students on niche topics and make them available to the whole world. Fellow who got Japanese internship, the fellow who got Rutgers TA-ship, remember that, okay? We are trying to build research groups, right? I showed you 124 flow sheets in chemical engineering. I locate all the people, they form a research group. I locate all the people who are doing eSIM circuit simulation across the country, we form a research group, because they have demonstrated that they are interested in doing this kind of work. We can work together. If there is a government project, big project, and say that, why don't you identify 5 people across the country, 5 colleges, who will I contact? I will contact the people who are already working with me, contact them and say, hey, here is a project, would you want to work together? Understand? So, we'll be happy to partner with like-minded people. Open source efforts are to continue. Open source efforts are not only idealistic, but make economic and commercial sense as well, right? Remember, I say that Scilab is better than MATLAB for you people. For most students, that's good enough. Only when they write really sophisticated code, they may need some toolbox which may not be in Scilab. But for most people, 99% of the people, it's more than enough. So it makes economic and commercial sense as well. So these have the potential to empower all children to collaborate and help them build virtual research groups that I talked about. So IIT Bombay is working on several open source projects. We invite you to join us. So we are funded by National Mission on Education through ICT, and also Pandit Madan Mohan Malviya, National Mission on Teachers and Teaching. So now I'm going to ask I'm going to introduce my team members who will, can you all come? Come here. In one go, I'll introduce all of you. They are the people who are going to give demos. We also have managers here. I will introduce them to you later. So we have Biswarup, we'll go in the same order. OpenModelica power system simulation, he is going to give a demo. He has worked on this Open IPSL, part of the team that in fact implemented Open IPSL on top of OpenModelica. And then we have Reom, who is a chemical engineer. He is the author of 2 papers that I showed, journal articles. He is going to give a demo of OpenModelica. He will take some simple equations and then show how to solve them, differential equations, and show how to solve them using OpenModelica. Okay. Then we have Saurabh. He is going to give a demo of electronic circuit simulation, eSIM, electronic circuit simulation. Then we have Siddharth. Siddharth is going to give a demo of XCOS. Have you heard of XCOS? Does anybody know XCOS? Okay. XCOS is the equivalent of Simulink. Simulink runs on MATLAB, XCOS runs on Scilab. So we have created XCOS on the cloud. So which means even using your tablet or your mobile phone, you can run XCOS simulation by using the cloud. He's going to give a demo of it. We have more than 100 examples already available from textbooks. Yeah, textbooks. We hope to connect it with our Scilab textbook companion later so that we can actually have that. So he will give a demo of that. We also have our managers. We have Sunil Shetty. So he helped develop this XCOS on cloud. He's our senior manager. We have Vinita. Vinita is our manager. She helps coordinate, overall coordinator, but she also takes care of Scilab, Scilab textbook companion, Scilab lab migration and so on. But she helps the Fossee project. You have already met Qasim. Qasim is our publications, public relations, PR, and he's also taking care of our laptop and so on. So this is our team, okay. We have a team of, in Fossee alone we have about 50 people. In spoken tutorial we have about 70 people. So I don't want to scare you by bringing all of them here, okay. But they will give a demo. That's why I have asked them to come. Is it okay? So you will start? Okay. Is there anything else I missed out? You will give a, he can also give a demo of Fossee optimization toolbox if you want. Yeah, because he coordinated that. Okay, remember I talked about toolbox. I told you that it is better than MATLAB optimization toolbox. You can ask him why. We'll explain. Okay. So all yours. Civil engineering, we are working on a software called Ozdag, open source software for steel structures, Ozdag. It's also available in fossee.in. In case you are interested, all the information is there.
Hi everyone, my name is Reom Certificate and I am going to talk about this software called OpenModelica. So basically Modelica is a modeling language, a programming language. Okay, it's a equation oriented multi-domain programming language, and OpenModelica is an open source implementation of Modelica. So Modelica has a lot of commercial implementations as well. If you have heard of Daimola, so that's one of the commercial implementation of Modelica language. And then we have OpenModelica, which is the open source implementation of Modelica language. Now, what makes this language different from other programming languages is something that I'm going to talk about. Right. So primarily, Modelica has two advanced features. Firstly, that is, Modelica is based on equation oriented. When I mean to say equation oriented, I want to differentiate it from algorithmic, there are two kind of equations basically, if I have to say. So now there are two different ways in which we can write an equation. Okay, so Modelica generally prefers this style of writing, and I'll explain why. Because when you say equation, in this particular equation, I can have any of the two variables as unknown, any of the two variables as known and one as unknown, and then the equation can be solved, right? But when I write this style of equation, I must have A and B as known to compute C. So this is basically an assignment where I want to say that my A and B should be known and I'm computing C, which is not OpenModelica do. OpenModelica follows an equation style where I can just write this equation irrespective of my known and unknown variables. Okay, so basically I need to write an algorithm as to what is my known and what is my unknown. When I write an algorithm, I always have my unknown on the left side of the equation and known on the right side of the equation, which is not the case with Modelica. Modelica, I can just write the equation, and depending on the type of model or depending on the type of information that we have, we can just say that okay, this is my known variable, this is my unknown variable, and I can simulate and give you the result. This is what the interface of OpenModelica looks like, and it has a lot of other components. OpenModelica, something called as OMEdit, OpenModelica Connection Editor, OM Python, which connects OpenModelica with Python. I'm going to talk about, give a demo on this OMEdit because it's a graphical user interface. So basically, in this, we have something. When we open the OpenOMEdit window, this is something what it looks like. So we have a libraries browser where you have all the libraries that you want to use or that you want to create or something like that, which is listed here. All the working files will be listed in this libraries browser. And then we have the recent files as to what are the recent files that you have opened and all, right? Then we have something called as message browser. So whenever you are, simulating something, right, we have a message browser. So it will constantly give you message whether your model is okay or not. If it is not okay, what are the errors it is throwing? So that all comes under the message browser. Now, this is a modeling perspective where we generally write the code and equation and everything. Okay, so I'll come to this part a bit later. And then we have plotting perspective. In this plotting perspective, basically we have our variables browser where whenever we simulate a model, we get the results. All the variables will be shown here and their values. And then if you want to plot any variables, that is being plotted here in the plotting perspective. Now, I'll just write to start with, I'll just write a very simple program, okay, so that you get to see that what Modelica can do. And traditionally in any programming language, the first program we write is hello world, right? But then Modelica is not hello world, and we print the string hello world, but Modelica is not for that purpose. Modelica is an equation based language. So we'll write a program hello world, but instead of printing the string hello world, we'll try to compute a differential equation, a very trivial differential equation. So I just created a class in Modelica called hello world. So I'll define my variables. So I'll just explain what I've written here. So nothing, it's just a very basic equation where I'm trying to solve dx upon dt. This is equal to a into x. That's all. That is what I'm trying to solve here. So if a is known to me, then I just write it as a parameter because a is known to me. So I just parameterize that particular variable, and then if whatever is unknown is just defined as a variable which is real, right? And then under the equation section we write the equation. So basically in Modelica, whenever you have to write a differential equation for the derivative term, we use the variable der. So that just says that it is derivative with respect to time. And by default in Modelica, the derivative is always with respect to time. Alright. So this is what my program looks like. Just a simple trivial equation, differential equation solving. Okay. So when I have to solve a model, basically there are few parameters that we need to give. Okay. So Modelica is mostly for kind of dynamic systems. When I mean to say dynamic system, any variable that is varying with time is said to be dynamic, right? I mean, if you talk of any system in real world, right, either natural or man-made system, every system is dynamic, right? They seems to be changing with respect to time. So that's why we talk of dynamic system here. And therefore, when you talk of dynamic system, when you have to simulate a dynamic system, you need to give as to for how much time you want to simulate the model, right? 5 minutes, 10 minutes, 100 minutes, whatever it is. So we have start time, stop time, and then number of variables. So whenever you simulate a model between some particular time, you need to simulate it for particular number of points, right? I want to simulate this model from time, for one minute, for 100 intervals, for 200 intervals. So this particular will give me the number of intervals. Okay. So now this is something very simple. So why do we need Modelica for this? Okay. So to answer that question, basically Modelica is mostly suitable for physical modeling. So when I mean to say physical modeling, if I have to give you an example, let's take a very basic, RLC circuit. Okay, so let's say I want to simulate an RLC circuit in OpenModelica, and the way I simulate it, any kind of block oriented, is that you will have a sine block, a capacitor block, different kind of blocks you'll have, and then you connect, and it's a kind of bit confusing. But when I come to physical modeling, the model as to how it looks will have a direct relevance to OpenModelica. Just to give you an example, let's say I want to simulate an RLC circuit. So I have a resistor here, and then I have an inductor, right? And then I have a capacitor, and then it is connected to a voltage source. Okay, so this is my ground. So let's say I want to simulate this particular block. Okay. Now when I want to simulate this particular block in OpenModelica, the way you simulate in OpenModelica will have a direct relevance to this particular picture. So when you see this, and when you see how we have simulated in OpenModelica, you can easily understand as to what has happened here. Okay. Before I go to modeling this particular block in this fashion, okay. So this is an example where I can have all the equations, all the models, everything in a single. All the equations for resistor, for capacitor, for inductor, for voltage source, everything in a single model, and I can simulate. So this is one way. Okay, but this is not how, why Modelica is made for. Modelica is made basically for, creating different small models, and then you integrate them together in a single environment and simulate, right? So to give you an example, I have my, this particular package circuit RLC called, particular model called circuit RLC, where I have my different components, resistor, capacitor, inductor, ground, everything. And then I just, drag and drop them, connect them to build a circuit. So I'll just try to show you as to how I build this circuit. So you see this is a, this is where I'll try to build my circuit from different resistor, inductor, capacitor and everything. So I have my models ready here, the resistor model, capacitor model, inductor model. So you just drag and drop them to So I've taken my resistor, my capacitor, my inductor and voltage source, and then also add a ground source. So we can, create this particular circuit here, if you just see. No, so yeah, we have inbuilt library also, and this is something that I've created. So I'll just show you the equation after I finish this. So it doesn't have all the equations for a particular RLC. You can, use the inbuilt RLC, whatever is available, or you can create on your own also. So one of the advantage of Modelica, as I said, is it is a multi-domain software. By mean to say multi-domain software, it has libraries of thermal, mechanical, electrical, and you can take models from each of these, integrate them together in a single model, and you can solve it. So you can see my circuit looks exactly how it is. I have shown it in my figure, and then you can simulate the circuit to get the result. You just get simulated, and you have all the results here in the plotting perspective. Right. So one of the main criteria for any model in OpenModelica to get simulated is that, before the model starts simulating, OpenModelica will check for degrees of freedom. By mean to say degree of freedom, I mean to say that my number of unknown variables must be equal to my number of equations. Okay, that is the only criteria that Modelica checks before it tries to solve an equation. And then once that's satisfied, it starts simulation and give you the result accordingly. So this resistor, capacitor, all these blocks have been built here, and all the governing equations for these blocks have, for this particular model have been written inside the block. So this is how we work with Modelica in general. It has a lot of different libraries. So it has a lot of, the inbuilt Modelica library has got electrical library, magnetic library, mechanics library, fluid library, thermal library, different things. So you can just go ahead and explore all these things, and I think whatever you want to simulate or whatever is of your interest, you can be found here. So if you go to these libraries, you have the inbuilt examples of all these libraries, right? So this is basically an example of a pumping system. Okay, so the idea is that, you have all these particular libraries and, multi-domain libraries. You can just take them, mix and match with each other and run it. So that is basically the idea. Obviously, you can go ahead and explore it from your side. Due to time restriction, I'll hand it over to my colleague Biswarup, who will take you through the OpenIPSL library of OpenModelica. Okay, and he'll give you more about it.
So Priyam has already discussed about the OpenModelica. So now you know about the OpenModelica interface. This is how it looks like, and this is the follow my cursor. So this is the library browser. He has already explained to you. But one thing I want to explain, that OpenModelica is a tool. This is not a language. Okay. So OpenModelica is based on the Modelica language. So this is the basis of the OpenModelica. So the main feature of OpenModelica is that it allows you to model from multi-domain point of view. So we try to tell you about what multi-domain is. So the multi-domain is that. So one more thing, very sorry to say, please take away your sight from mobiles. When I was standing here, I found many of you were playing with your mobiles. Please don't do that. So multi-domain modeling means you have access to models from various engineering domains. That means, so when I write the term multi-domain modeling, so you have the term multi-domain. Multi-domain means you have different engineering domains, not only the electrical engineering. So you can couple models from different engineering domains, like you have the chemical, electrical, civil. So everything you can do using this OpenModelica. all type of modeling can be done using OpenModelica. So for the electrical engineers, the most important thing is that the application of the OpenIPSL library. So if you go to this website, how many of you know about GitHub? Very few, right? All right. So we host this library on GitHub. So you have to go to just in case if you want to have more details about this library, you can go to this website and take a look at it. And also we have everything under om.fossee.in/. So you can take a look at some simulations at om.fossee.in/power systems. We host some simulations there. So now what I will talk to you about the OpenIPSL library. As you can see, so what it is? It's a 9-bus test system, right? I hope the electrical engineers know about it. So this is what we are trying to simulate. We are trying to build this model, taking advantage of some components from 2 libraries. So one is the Modelica standard library. I think PM has already explained to you. So one is the Modelica standard library. We call it MSL. So we call it MSL. That means the Modelica standard library. That is integrated with OpenModelica interface. So this is the Modelica standard library. As you can see, this is the library structure. So when we try to develop some models in OpenModelica interface, we have to take some components from this library as well. For example, if I open this class, for example, this is the generator model, all right? So the switch component and different blocks, for example, the constant blocks, step blocks, these have been taken from the Modelica standard library, MSL, okay? And the other components, for example, AVR2, and I hope you know AVR2, right? Electrical engineers? All right, so AVR and generator models are taken from the OpenIPSL library. So we actually couple 2 things here. We take some blocks from the Modelica standard library and we take some components from the OpenIPSL library. OpenIPSL stands for Open Instance Power System Library, which is a library for power system simulations with the concept of phasor time domain simulations, all right? AVR means automatic voltage regulator. You are from electrical engineering, right? So you know these terms. All right, so AVR means automatic voltage regulator, and you have the order 4 generator model, and this model comes under PSAT. So I hope you know PSAT, right? You don't know PSAT, all right. So PSAT stands for the Power System Analysis Toolbox that is compatible with MATLAB. So we have all the models from PSAT available in OpenIPSL library. So PSAT is something proprietary because you should have, I mean, I won't say that it is proprietary, but it is somehow proprietary because you sometimes need MATLAB to run some models from PSAT. But now we have all the PSAT models included under this OpenIPSL library, all right? So this is the most advantageous thing. So and OpenIPSL is an open source library, so you have all the models available, so you can just drag and drop in OpenModelica and you can run the same simulations. So now you know the Modelica standard library structure, all right? And this is the OpenIPSL library structure where you have some, all right. So just take a look at the library browser. You can see the OpenIPSL library. So it has a puppy logo, and there are some examples available under this library. Different types of examples. For example, you have this, you know PSSE, right? So PSSE is a power system simulations software for engineering, and it is provided by Siemens. So this is a paid version. You have to pay like $300 for it, but Now you have all the models included under OpenIPS library for free. This is the advantage, all right? So once you take a look at this library structure, you have all the different examples. So GenCell is the salient pole generator model, which is available under PSSE, and you have the same model here under OpenIPSL. The most advantage of OpenModelica is that it's a equation-based modeling language. So you can actually go inside every model and you can take a look at what it is inside. For example, if I want to understand what do you have inside this GenCell model, for example, or whatever, in general, if I want to go inside this, as Reom has already explained, if I want to go inside this model, this is actually a written code behind it. And you can access all the components from both the layers. You can access the entire model from each of the sub-components. So, for example, this is a single machine infinite bus system, right? I hope electrical engineers know it better. So, you have the single generator at one side of your system, and then you have a load connected, and then you have the entire power system simulation connected to your infinite bus side, all right? And we try to simulate it for, there is a fault simulated in the bus number, for example, 3, and this is how we do it. Now the advantage is that if you want to access this model, just go to open class. So this is the diagram layer. But if you want to access the equations of this model, then you just have to go to the text layer, and there you have all the equations listed. So the main advantage of this language is that the components are not a black box to you. You can actually go inside every model and modify as per your requirement. What used to happen in Simulink and other software is that you do not have access to models. I mean, what is written inside the models, right? Now you have access to equations, every single equation. You can modify all the components as per your requirement. It is a Modelica language. I mean, OpenModelica is a tool, okay? So OpenModelica is a tool, and it is based upon the Modelica language. And Modelica is a open source language, okay? And you get access to OpenModelica through the OM edit. OpenModelica actually has a very strong compiler called OMSC. I mean, OpenModelica compiler, OMC we call it, and it is actually the core of OpenModelica. So before you run simulation, OpenModelica compiler compiles every model and gives you the solution. All right. So this is a tool. So it allows you to do the multi-domain modeling using the OpenModelica. Now I will just try to give you an illustration using the 9-bus test system so that you can understand what it is going on. Now I have this model. So for example, I want to see what it is inside this generator 1. So we have the 3 different generators at 3 sides, right hand side, left hand side, and you have the one at the bottom. And for example, you want to ask me that what is inside this generator model. So how do I access that? I click on it and I go to the open class. And this is the text layer. And also you can take a look at the model layer. Alright. So Modelica basically allows you to model anything from 2 different layers. One is the modeling layer, another is the text layer. So now we have time shortage, so I will just run the simulation so that you can take a look at it. So you go to the simulation button and I click on it. The main advantage of OpenModelica is that it distinguishes the model from the solvers. Alright. This is a very important feature of OpenModelica. So the model is separated. So when you try to run a model, it should run with the different solvers. Sometimes the solvers are implanted within a model. So you never know. If you have a black box model, you never know what kind of solver you are using. But OpenModelica allows you to identify the solver and solve the same model using different solvers, right? For example, when you go to the simulation setup here, just follow my cursor that you have the different methods, right? For example, you have Euler, Dassault, and you have other different types of Rangutta order 4, 3, 2. You have different solvers here. To run this simulation of this 9-bus test system, I hope you can follow me. We use these predefined settings and we just we are just trying to simulate it for 20 seconds, starting from 0 to 20, all right? And with the number of intervals to 20,000, with this tolerance and everything. So when I run it, I press OK, and the OpenModelica compiler starts acting now, okay? So it starts compiling your model. So the simulation happens in two procedures. The first procedure is that it starts compiling your model. Then upon the compilation is done, a C code is generated, okay? So once the compilation is finished, then the simulation starts. You will eventually see how it works. Just take a look at it. Now you have the compilation running. It is compiling the model. So when it will execute the compilation, it will start simulation. You will eventually see, yeah. All right, I mean, I use MATLAB, but I'm not that much familiar because I use mostly for coding. But see, in open source, I mean, MATLAB is not open source, right? So that's what Professor Kannan was explaining to you, that you should use Scilab, because Scilab is the alternative for MATLAB, all right? But the advantage of OpenModelica is that you can actually see, sometimes you have the solvers implanted inside the model. So you never know what is the model based on, whether it is based on solver or not. But entire model, when you try to simulate some entire model in OpenModelica, you have the entire model distinguished from the solver. You can have different results based on different solvers for the same model using OpenModelica, and you can identify the differences. So as you can see that it has started the simulation, okay? And it has executed the simulation. So now you have the variables here, and this is the plotting browser. Reom has already explained it. Now I just want to take a look at the, so as you can see, I have this bus number 9. It is my point of interest, and because we are just trying to simulate a fault here, 3-phase balanced fault here. So for your understanding, I will just go to bus number 9 voltage, and I will try to understand what's going on. So this is my variable browser, and I go to the bus number 9, V9, and I go to V, all right? So I'm interested to see how the voltage behaves for the bus voltage, bus 9. So this is the simulation result. As you can see, for first few seconds, you have the stable system, right? And when you have this fault, you have this sudden dip in your voltage, and then you have some controllers inside, like AVRs. So it is regulating your voltage, so it goes back, and after some oscillations, it stabilizes again, right? So this is the importance of OpenModelica. So you have this entire simulation running in PSAT and PSC as well, but we try to use OpenIPS library, and we try to integrate it with MSL, and this is how we simulate a 9-bus, and even we have simulated the entire European network. So we have like Nordic 44 and so many different systems. Some of the examples are available under this website. You can take a look at it. And there are some advanced modeling using the multi-domain. I will not go into that much detail. So now Siddharth will, or you will come, all right.
So some of the features of eSIM, so I have just a simple circuit of a stable multivibrator using transistor. As you can see, you can the basic components are already available in eSIM libraries, like your basic semiconductor devices and other components, transmission lines and everything. So these are all present in eSIM. So all you have to do is connect them, create a netlist. We have a function called KiCad to ngSpice. So in this you can set the parameters. You can choose the type of analysis you want to do, AC, DC operating point or transient. So I have taken transient analysis. I set the parameters for it. Then I type in the source details. Then this device modeling. What this does is here in this circuit I am using 2 LEDs and 2 transistors. So I need to provide a spice file for it. So for that spice file, I am giving this, if you can see the extension, d.lib and npn.lib. So these are default libraries that are present in eSIM that you'll use. Okay, I'll just click on convert. Okay, I can see the simulation output for it. So let's just focus on this one. If you see this curve, the peak voltage is currently 8.75 something. So in order to, you want students to know no, I don't, what happens if you use a different diode? What happens if you use a different LED at the stable multivibrator? Then what happens? You want them to show. So you can give them as an exercise saying okay fine, don't use this, use some other diode. So I'll do the KiCad to ngSpice conversion one more time. This time I'll use a different, I'll use the spice file for an LED. Right now I was using for a diode 1N4148. So I'll use an actually LED diode spice file. You can see the output voltage has gone down. It was earlier 8.75, now it's around 7.5. So how do you upload these files? The spice files, you can do that. We have a feature called, what makes eSIM unique is you can add your own spice files to us. So there's a feature called device modeling. Using device modeling, you can upload your diode, you can upload your BJT, MOSFET, etc., etc. You can place these files. You can alter the parameters of it. Reverse saturation current, some internal capacitance. So if you are getting some fluctuation in the circuit, you can actually edit these parameters and show that circuit to the students. Or you can give this as an assignment to your students, telling them, see how this works. You can take an example from any textbook, and this is applicable for both. Like for this is I'm saying for analog electronics. For digital electronics, you can change some parameters in the gates, and then we can see the output. Yeah. So this is a simple 230 volts to 5 volts regulator. So this is most commonly used in most of the electronic circuits. We will definitely use it. So you can simulate this using here. But the problem is how do you get the 7805 to work? It is not a basic component. So how do you design that? So we actually had a student who submitted a design to us. I will just show that design. If you have an extra smart student who is not impressed by a stable multivibrator, ask him to build an IC. So that's the idea. And that's the advantage of eSIM. You can upload your own semiconductor models, and secondly, you can upload your own circuits. You can make your own circuits, make alterations to them, and use them in your projects. Secondly, once you successfully simulate these things, you can go for PCB designing. So I will open another project for which I have done the PCB design for this. So it accomplishes all the goals. You can just give one circuit, ask them to simulate it, get the plots, and after the plots you can ask them to go for PCB design. You can ask for various things, DRC, then you can explain how the tracks are laid out, why certain things have to be the way they have to be. So you can, there are actually some ICs present. So the subcircuit file which I showed you right now, so you don't necessarily have to make the internal connection, because just the 7805 has about 20 plus transistors. So not necessarily you have to do that. There is a .sub file which is a .subcircuit file. So even if you have that file and upload it using that option, it will work. And the subcircuit files are mainly available, but still sometimes you will face a problem that something. Yeah, general ICs are there, and if you don't find any ICs of your use, let's say something is missing, 7812, 1117, something else is missing, you can email to us, or you can ask your students, or yourself can design it. We are here to help you. Okay, the site is esim.fossee.in, so it's present on the Fossee website.
Karan sir explained Scilab and XCOS. XCOS, which is open source alternative to Simulink, is being promoted by Fossee, and we are providing an online version for it. This is the online version for the Scilab tool XCOS. You don't need to download Scilab, you don't need to install anything. You can just go on to our website, xcos.fossee.in, and you can use XCOS as it is. We have about 130 examples available on the website, which you can use for practice in your classrooms. It is a smaller scale equivalent of our textbook companion project. I am going to execute a couple of these examples to give you an idea. The first of these is a implementation of an underdamped RLC circuit. Again, for the electrical engineers, as you will see, an underdamped RLC circuit. The next of our examples is a state response, response time for a control system circuit. And this is something I'd like to point out for our cloud system. We can actually write scripts to drive the XCOS files. Like, you can specify a variable in a Scilab script, and you can have that variable come up in an XCOS file to use it. So, if you look at the script, we're defining a basic signal and a transfer function. We execute the script. You can look at the transfer function here. Frequency oscillation, the value of k, overshoot, etc. And this is a basic CLR system, a linear response system. And there we have it. We have electrical toolkits here as well. This is a synchronous machine example, an alternator, the number of poles. So yeah, you can use this in class. This is actually where Scilab stands out compared to MATLAB. We have high quality online tools that do not require an installation, are free of cost, and available freely without any installation. How many of you have had courses in convex optimization, operations research, or operation theory? Yeah. So this is the tool for you. This is the Fossee optimization toolbox. I do hope you can see the writing on the screen. We developed this to integrate a lot of open source solvers such as the ones available on CoinOR, others like IPOpt, Symfony, and what we're integrating next is Cohen for constrained quadratic programming. We currently have solvers for linear programming, nonlinear programming, integer programming, both linear, nonlinear, and conic programming. All of these are completely open source, free of cost and free for modifications as you will. I'm going to build and load a toolbox. For this, this is running locally. Xcos on web is what you don't have to install. So this is that. This you don't need to install. You have the palette here. You have the palette here. You have the workspace here. You can simply go to the website xcos.fossee.in and take up a couple of components on the palettes, hook them together, and get it running. This is the you can modify it as you will, like it is similar to OpenModelica but at a smaller scale because it's not supposed to do everything Modelica does. So you can modify everything accordingly. Now, locally the toolbox has been built and loaded. I'll show you a couple of examples for linear programming. This is the example we'll be solving. As you'll see, very basic linear programming example. Two variables, you need to minimize it, subjected to 4 inequality constraints, and the objective function is defined as such, as a row vector. The constraints are defined as A and B, a matrix for the left hand side and a vector for the right hand, a column vector for the right hand side. And now we execute it. As you will see, we have an optimal solution. These are the values for x you have to assume to get the best possible outcome for f, for the minimization. This is linear programming. This is fully constrained non-linear programming. This function. As you will see, another basic example. A non-linear objective function subjected to, this is the objective function, x1 square minus x1 x2 divided by 3 plus x2 square. A non-linear objective function, as we know, is not as easy to resolve using simplex or even primal or dual methods as linear problems are. For this, we use IPOpt, the interior point optimization technique. This is the objective function. We are currently using only linear constraints, as I just explained. This is the left hand side of the constraints. This is the right hand side of the constraint. And because it's non-linear, we are providing an initial point. These are the values for x for which we can get the best possible outcome for this minimization. The toolbox is currently available for Scilab 5.5.2 via Atoms and on Scilab 6 via the Fossee GitHub repository. So you can download it from either of those choices.